We know from things we've done earlier in the unit that charge can build up on or in an object. Today, what I want to do is focus on what that charge distribution is going to look like. Where are the charges going to go, and what is it going to look like when they go there? Everything that we talk about today for the rest of the day is going to involve a conductor. Understand that. Okay, if I'm talking about charge distribution, charges rearranging, doing their thing, it has to be a conductor, because with an insulator, all bets are off. Charges can move around a bit, but not to the degree they can on a conductor. We're going to assume everything that we talk about today, the charges are free to move. They're free to roam. If there's a force that pushes it to the left, then they'll move to the left. All right? So what happens when charge builds up on or in a conductor? Where does it go, and what does the distribution look like? Well, there's a term that we have to understand first, and that's called static equilibrium. Static equilibrium exists when something is at rest because there's balanced forces acting on it. When electrons push each other away from each other, you get a buildup of electrons on or in this conductor. These electrons are going to push each other away. So there's repulsive forces all over the place. They're moving around all over the place. But at some point, they're going to reach a point where the forces balance out, and then they're going to remain at rest. That's static equilibrium. It's kind of analogous to an awkward party in a small room. You've got 30 people all in a small room. They don't particularly care for each other, these 30 people. They don't want to make small talk with each other, so they're repelled by each other. They don't literally push each other away, but they try to get as far away from everybody else as they can. And that takes a little while. Okay? I see somebody over here, I don't really want to talk to him. And I see somebody over here, I don't really want to talk to her. So I move as far away as I can. But the problem is, when I move further away from one, I end up moving closer to another. At some point, though, I'm going to find a spot. All right, this is my spot. At some point, everybody's going to find their spot where they're the most comfortable. That's when we're in static equilibrium, when all those repulsive forces end up balancing out. Electrons do the same thing. You got a bunch of extra electrons on or in a conductor. These electrons will push each other away until all the forces balance out and they reach this point of static equilibrium. Does that make sense? This doesn't happen in non-conductors, right? It doesn't happen in insulators because the electrons don't move as freely as they do in conductors. Remember what we said a minute ago. Everything we're going to talk about today is going to involve conductors because the electrons can do what they need to do in conductors, not so much so in insulators. I want to take a look at a few specific shapes now to examine the charge distribution on or in. First is a solid conducting sphere. It's like a marble or a billiard ball, except it's made out of metal, some kind of conductor. Let's say that we have 3 excess electrons on this. We could have 1,000,000. The analysis would be the same. It's just easier to understand the diagram if we have 3. We don't have arrows going in 1,000,000 different places. We have arrows going in 3 places when we have 3 excess electrons. Now understand as well that I draw it with 3 excess electrons. That doesn't mean there's 3 electrons. There could be 1,000,003 electrons. But if there's 1,000,003 electrons, there's 1,000,000 protons. We have 3 excess electrons here, coming from wherever. Okay, maybe I rubbed it against something that caused it to develop a charge. Maybe it got struck by lightning. However it got the charge, it's got 3 extra electrons. Now I want to look at what happens to those 3 electrons. And by extension, what would happen to the other 1,000,000 extra electrons if I had 1,000,003 excess electrons. Let's number these electrons here. 1, 2, and 3. Charge number 1 experiences a force because of number 3. 3 repels it and pushes it this way. It also experiences a repulsive force because of number 2. 2 repels it and pushes it this way. Now, if I have 2 repulsive forces acting on number 1, the net force on number 1 is going to be this way, somewhere in between. Similarly, charge number 2 is going to experience a repulsive force caused by number 1, and it's going to experience a repulsive force caused by number 2. It's pushed away by number 1 and by number 2. Sorry, by number 3, I should say. The net force is going to be somewhere in between, somewhere like this. Number 3, same thing. It's pushed away by number 1 this way. It's pushed away by number 2 this way. And the net force on number 3 is this way. What do you notice about all three net forces? All three unbalanced forces. What, pardon me? They're all pointing outwards, yeah. All three of these electrons get pushed towards the outside. It's exactly what happens. If you have excess electrons, whether it's 3 or whether it's 1,000,003 excess electrons, if you have excess electrons, they're all going to be pushed to the outer surface of the conductor. You got that? All going to be pushed to the outer surface of the conductor. Now, take a look at the distribution, the spacing of them, the spacing between 1 and 2, the spacing between 2 and 3, the spacing between 3 and 1. The spacing is equal as well. If you have a uniform shape like this, they're going to be pushed to the outer surface, and the distribution is going to be even. They're going to be evenly distributed, equidistant apart from one another on the outer surface. So are you going to have electrons in this solid conducting sphere? Yes, but only electrons that are balancing the protons. No excess electrons inside. They're all the excess ones are going to the outer surface, and they're going to be evenly distributed on the outer surface. Now the second diagram, all it's meant to show us is the electric field. This electron produces an electric field this way. This one produces an electric field this way. This one produces an electric field this way. The net electric field ends up being toward the negatively charged object. And of course, at all points, it's perpendicular to the surface. Now let's take a look at our second shape. Our second shape is a flat conducting plate. It's uniform as well. It's not uniformly round, it's uniformly flat. What happens to the excess charges here? Well, let's number these again. 1, 2, and 3. Charge number 1 is pushed away by charge number 2. It's repelled by charge number 2, pushed to the left. It's also pushed away by number 3. So if you take a look at this force that we have labeled right here, that's actually a combination of the repulsive force caused by number 2 and the repulsive force caused by number 3. It's pushed to the left as a result of both of those forces. Now, number 3 is pushed to the right as a result of number 2 and as a result of number 1. Now, that's a smaller force because 2 and 1 are closer together than 2 and 3. But those aren't the two charges that I want to focus on here. I want to focus on charge number 2. Charge number 2 is pushed to the right by number 1. We'll call that F12. And it's pushed to the left by number 3. We'll call this F32. Why is F12 bigger? We have it drawn bigger, and that's correct. But why is it bigger, Jade? Closer. Yes. 1 and 2 are closer than 3 and 2. Therefore, force of 1 on 2 is going to be a bigger force than the force of 3 on 2. All right? What's going to happen to that charge, number 2, as a result of those two forces? What's going to happen to it? It's a conductor. Electrons can move around wherever they want, right? If it was an insulator, all bets are off. But if it's a conductor, they can move around to wherever they want to go to. Where does it want to go? If you have a force that's to the left and a force that's to the right, and the force to the right is bigger than the force to the left, Jade, where does it want to go? Right. It wants to go to the right. Now, as it goes to the right, what's going to happen to the value of F12? Right? Pardon me? No, F12 is not going to increase. As you get further away from number 1, it's going to decrease, right? F12 is going to go down. What's going to happen to F32? As you get closer to number 3, F32 is going to increase now, right? So 1,2 is going to decrease, 3,2 is going to increase. At some point, those two forces are going to be equal, right? Where do you think that's going to happen? When are those two forces going to be equal to each other, F32 and F12? Yeah, Connor? Yeah, when it's in the middle. That's when it's reached a point of static equilibrium. The forces have balanced, right? We've gone into that room with 30 people, a little uncomfortable. We're kind of trying to get as far away from everybody as we can. Okay, we finally find that spot where I'm repelled by this person equally as much as I'm repelled by that person. Okay, the force is balanced. I'm in a state of static equilibrium when this charge is in the middle. They are once again on the outer surface, and they are once again evenly distributed on the outer surface. just like we had with a solid conducting sphere. They go to the outer surface, the excess electrons, that is, go to the outer surface, and they become evenly distributed on the outer surface. Now, this next diagram is a little bit harder. This next diagram, we have a pointy object. We call it an irregularly shaped solid conducting object, but let's call it a pointy thing. A pointy conductor. If you have a pointy conductor, or a pointy thing, then the distribution is going to look a little bit different. I think they've overcomplicated things a little bit with their diagram. I'm going to simplify it just a little bit, and I'm going to label only 3 charges, 1, 2, and 3. And I want to focus on charge number 2. Charge number 2 is pushed away from charge number 1. We'll call that F12. Now, 1 is pushed away from number 2 as well, but it's not what we're trying to analyze right now. 2 is pushed away from number 1. 2 is also pushed away from number 3, but notice that's at a bit of an angle, like this. We'll call that F32. Now, because force of 3 on 2 is at an angle, I'm going to break it down into components. I'm going to break it down into an X component. I'll call that Fx. And a Y component. I'll call that Fy. So Fx and Y are the X and Y components of F32. This excess electron will go once again to the outer surface. And why does it go to the outer surface? Because the Y component, F32, pushes it to the outer surface. Right? There's one force pushing perpendicular to the surface, and that's Fy. It pushes it outward. F12 pushes it towards the tip of my pointy thing. Fx pulls it back from the tip. So you have opposing forces here, one that wants to push it out to the tip, one that wants to pull it back from the tip. Who wins? Who wins, F12 or Fx? Which one's bigger? F12. So this charge number 2 moves out towards the tip. Now, as it goes out towards the tip, F12 decreases as you get further away from charge number 1, right? It gets smaller. And at some point, F12 will be equal and opposite to Fx. They're going to balance each other. That's when you're in a state of static equilibrium. Where's that going to occur? Well, not when the charges are evenly distributed, but rather when these charges 2 and 3 are closer to the tip. In other words, they go to the outer surface, but we don't get an even distribution. We get a higher concentration of charge at the tip. That's why when you walk across the carpet, try to shock somebody, walking across the carpet here, walking across the carpet, going to shock Zach. I shock him with my finger. My finger, although it's not a great conductor, it illustrates what we're trying to show here because my finger is pointy. It's a lot more pointy than my arm, right? I don't walk across the carpet and say, I'm going to shock him, and then go up against him with the side of my arm like this. It doesn't work. It works like this because my finger is more pointy than the side of my arm. Now, you guys used the static ball, the Van de Graaff generator here a week or so ago, a couple weeks ago, and it worked well for a couple of you guys. The hair stood on end really nicely for some of you guys. When you had your hand on the Van de Graaff generator, there was a charge buildup in various parts of your body. But where was the strongest charge buildup? In your hair. Your hair is the pointiest part of you. It's narrow and pointy. So you had the highest buildup of charge in your hair. That caused your hair all to become negatively charged, and, well, they all repelled each other, and therefore they stood up on end because they were all repelling each other. If your hair wasn't so pointy, it wouldn't work so well. All right. So we've done 3 things so far. A uniform sphere, charges go to the outside and are evenly distributed. Uniform flat, charges go to the outside and are evenly distributed. Non-uniform, pointy, charges go to the outside and are not evenly distributed. They're more tightly concentrated at the pointy part. Now the last one that I want to show you here today before I show you a quick little video is what happens when I have a hollow conducting sphere. Now, I'm not going to go through the details of what the charge distribution is going to look like because the charge distribution is going to be the same as it was for a solid conducting sphere. There's something else that I want to point out about this one. You can see that, look, they've already got them drawn going to the outer surface. They go to the outer surface and they're evenly distributed. By the way, here's a quick question for you, little aside. Why don't they go beyond the outer surface? The forces are always pushing them out. Why don't they keep going once they get to the edge of that conductor? Why don't they keep going into the air? They do sometimes. But for the most part, they don't.
The air is an insulator?
Yeah, because the air is an insulator. If the air was a good conductor, then they would keep going, right? But they don't travel very well through the air because it's an insulator. If the air happens to be damp, then the air is a better conductor, and then you are going to lose more electrons off the surface. That's why I said we want to use the static ball, the Van de Graaff, on a day when it's dry rather than a day that it's humid, because we want the charge to build up on the static ball versus being discharged into the air. All right, back to this. You know that the charges all go to the outside. You can see that in diagram 1, and they're evenly distributed, just like they were in the solid conducting sphere. What I want to look at here specifically is diagram B. Diagram B, we have 3 charges all on the outside, a million charges, but 3 excess charges, all on the outer surface. They all evenly distributed. You can see the electric field lines are drawn here as well toward the negatives. Okay, it looks good. Let's draw the electric field inside. Inside. The field inside caused by number 1 is this way. The field inside caused by number 2 is this way, always toward the negative, right? The field inside caused by number 3 is this way. If we had 1,000 of them, then you would draw 1,000 different field lines, and it would look a lot more cluttered, but we would end up getting the same effect. If we were to do a vector analysis of this, a vector analysis where we took the x components of all of these vectors and then took the y components of all of these vectors, added up the x's and added up the y's, what do you think you'd get for an electric field? These 3 lines combined add up to give me 0. The net electric field inside this conductor is 0. We call this a Faraday cage. A Faraday cage doesn't have to be a perfect sphere. If you've got a conducting surface, the net electric field inside that conducting surface, no matter what, will be 0. This is why, contrary to what we've thought for all of the years of schooling leading up to grade 12, this is why a car is a safe place to be in a lightning storm, not because of the rubber tires, like we always think, right? Well, the rubber tires protect us, right? Listen, guys, electrons just made it from the cloud to the car. The tires have a ½ inch of rubber. You think a ½ inch of rubber is going to stop these electrons now? They just made it this far? Of course not. If the electrons can go from the cloud to the car, they're certainly going to go from the car to the ground, whether it's through the rubber tires or whether it's through the air. That doesn't stop anything. That doesn't make a car safe. So why is it that a piece of metal in a lightning storm ends up being safer than a non-metal in a lightning storm? Why is it that something that attracts lightning keeps you safer than something that doesn't attract lightning? Yes, the fastest route to the ground would be through the metal, and the electric field, this is the important part, the electric field inside that metal, inside that Faraday cage, which is the car, is 0. If there's no electric field inside that car, then you're not affected by it, and nothing inside the car is affected by it.